Hello, welcome back. We've been talking about sound, and one thing about sound I'm sure you've seen or heard before is the Doppler effect. What the Doppler effect is that if the source or the receiver is moving, the apparent frequency of a source seems to change. The frequency seems to change, right? And if the frequency changes, I didn't mean to have that there. If the frequency changes, the wavelength changes. So in the case of a Doppler effect, you have sound moving through a single medium. Now, I told you before that if the medium changes, the velocity changes. And since the frequency of a sound is determined by the source, if the medium changes, the wavelength changes. So if the source is not moving so if it's just a coherent source, the frequency is constant and the frequency is equal to velocity times wavelength. Okay. And if the medium changes, the velocity changes, so the wavelength changes. That's why sound sounds differently when you're underwater. Now, what happens though if the medium stays the same? So when the medium stays the same, the velocity is constant. But if I shouldn't say the velocity is constant, but the velocity of sound is constant, not the velocity of the object. So the velocity of sound is constant. So if the observer or the source are moving, the sound still moves at the same speed, but it gives an apparent change in the frequency and wavelength. All right? So in a given medium, velocity is constant. If the source is coherent and not moving, frequency is constant. Okay? So those are some parameters where you get constants. But what about when the source is moving in a single medium, and that medium is air? In that case, the velocity of sound is what's constant, and the frequency and the wavelength change. So let's look at that a little more deeply. Let's start by looking at this bug. This bug is in water and it's making waves. And you can see it's making 4 waves per second, right? 4 waves per second moving. As that bug starts to move, okay, as that bug starts to move, notice how in the direction of travel, the waves get compressed. And away from travel, they get expanded. So an observer would encounter a higher frequency as the bug is moving towards you and a lower frequency as the bug is moving away. So higher frequency here where they're moving towards you, and lower frequency here when it's moving away. Okay. We call that the Doppler effect. It's not that the source is changing. The frequency at the source stays the same. What's happening is the frequency that the observer is hearing is what has been changed by the motion. So basically you've warped space in a way by moving. Okay. And as you know, like a fire engine coming towards you, the waves are compressed in the direction of travel and they're expanded away from it. Okay. Now the Doppler effect doesn't just occur with sound, it can occur in water, as I showed you with the bug, it occurs with light. And because it occurs with light, when a light source is approaching you, the frequency increases. And when it's moving away from you, the frequency decreases. Now, lower frequency means higher wavelength, and a higher wavelength light is red, and a lower wavelength light is blue. Now, blue has a smaller wavelength, but it has a higher frequency. It's higher energy. Blue is a higher, ultraviolet is a high energy wave. Infrared is a lower energy wave. So since this is on the blue end and this is on the red end, and if something is moving towards you, you get this compression. When a light source approaches, we actually call that a blue shift. Increasing frequency is called a blue shift. Decreasing frequency, or you could say increasing wavelength, is a red shift. So if you're moving together, you see a blue shift. If you're moving apart, you see a red shift. And that's actually one reason that we say that the universe is expanding, because the farther away stars get from us, their energy has been shifted towards the infrared, a red shift. and that tells us that they are moving away from us, that red shift, and I'll show you why mathematically in a moment. Okay, so when a source moves towards you, do you see an increase or a decrease in wave speed? If it's moving towards you, think about it. Think about what I've already said. Frequency is determined by the source. If you change the medium, you change the velocity. Does the medium change in this question? No. The speed only changes if the medium changes. It is the frequency and the wavelength that change. So in both situations that we have, the wavelength is being altered. If you change the medium, if the velocity is constant, then the frequency and wavelength change, and the velocity is determined by the medium. Okay? If the source is constant, then the ratio of velocity to lambda, so when the medium changes, the velocity changes, and that causes a change in wavelength. If there's motion, the velocity is constant, but that causes the frequency and wavelength to change. So, and I'm talking about motion of the source or the receiver. So if there's motion, but the medium stays the same, velocity is constant, frequency and wavelength change. If there's no motion, but the medium changes, then the frequency stays the same and it's velocity and wavelength that are affected. So how does the apparent frequency of waves change as a wave source moves? Well, it depends. If it's coming towards you, if you're moving together, you get a blue shift. If it's moving apart, you get a red shift. And here's the actual equation for that that's not in this book because this is a conceptual book. There are two different versions. You usually see this version. I actually prefer this version, and I'll show you why. The equation is actually, this is the frequency of the source. The frequency of the source doesn't change. And this is the frequency that the observer hears. So if you are moving, if the wavelength is getting smaller, you're moving together. So if you're moving together, the frequency needs to get, the frequency should get bigger. If you're moving together, the frequency increases. So if the numerator gets bigger, then you're moving towards one another. If the denominator gets smaller, then you're moving towards each other. A bigger numerator or a smaller denominator is a bigger number. So what happens is you get these equations where here's the velocity of the observer and here's the velocity of the source, either way. This velocity is the velocity of sound in that medium. That velocity is going to be constant. It's usually 343 meters per second in air. That's what sound moves. This is the velocity of the observer. If the observer is not moving, you just don't use that. So you just have V over V plus or minus Vs. And if the observer is not moving, if the source is not moving, so you have the observer and the source. If neither one is moving, you have V over V, which is 1. Frequency of the observer equals frequency of the source. If you're not moving, you hear the sound as it was intended. But if the observer is moving, you have this factor here that changes the relative velocity. And if the source is moving, it changes the relative velocity. And you can use this equation to figure out what the frequency of the observer will be. And like I said, if you're moving towards, the numerator gets bigger, the frequency gets bigger. If you're moving away, then the frequency gets smaller. So it's really like right in here is what you guys want to know. If I decide to put a Doppler effect question on the test, I'll give you a written example and I'll put that in the notes. But for now, I just want you to know the conceptual aspects. Now this last little bit just has to do with two types of waves. I just want you to understand what these mean. When the speed of the source in a medium is the same speed as the waves pile up. So notice how all of the waves are to the point where in the front, the wavelength seems to go to 0. All of the waves are adding together. That is called a bow wave, when the waves are adding together. Same thing happens when an aircraft travels at the speed of sound. Now, the moment that aircraft it goes faster than the speed of sound. The moment it goes faster than the speed of sound, the crests overlap at the edges, and the pattern of overlapping crests creates this V-shaped wave. It's this V wave, that's the bow wave. So a bow wave is that V wave that kind of travels behind something, right? You've probably seen this in a speedboat with you see the two wave crests pushing back behind it. That's a bow wave. If that boat could travel at the speed of sound, then what you get is something different. So notice here, V is less than the V of the wave. When V equals V of the wave, that's right when you hit that crest. And when V is greater, that's when you get that bow wave, right? So you're actually going faster than the wave around you. That's a bow wave. And the bow wave that you're most familiar with probably is a shock wave. A shock wave occurs when an object moves faster than the speed of sound. And don't remember, this isn't a two-dimensional thing. It's three-dimensional. It's like a cone. It's a conical shock wave. And there's a lot of energy in that shock wave. Okay? And that's what that energy is what we recognize as a sonic boom. So the sharp crack heard. Okay, so those you just need to know the definitions for. So what causes a shock wave? Going faster than the speed of sound. What causes a bow wave? Going faster than the waves around you. So you can get a bow wave in water, but shock waves are generally just referring to sound. All right, let's see what you guys have learned. The time it takes for a pendulum to swing to and fro is called its. Now this is not how many times it swings back and forth, but how long it takes it to swing back and forth one time, and that is the period. The frequency of a wave is the inverse of its period. Frequency is inverse of the period. A wave transfers, basic definition of a wave, it transfers energy. The speed of a wave can be found by multiplying its frequency times f lambda wavelength. The vibrations along a transverse wave, so the wave moves this way, are they moving the same direction, perpendicular, parallel, along? Are they moving with the wave? So if it's a transverse wave, that's the sinusoidal. So the wave is going up and down, which is perpendicular to the direction of travel. And longitudinal are the opposite. That is a parallel to the wave. Interference is characteristics of all waves. All waves can have interference. Standing waves appear to be constantly moving, are the result of waves overlapping in phase and out of phase, form only in multiples of 3, do not increase with increasing frequency. So what do you guys think? B, are the result of waves overlapping in and out of phase. Because remember, you get the out of phase nodes where there's 0, and then you get overlapping in phase where you get different levels of constructive interference that are making it go up and down, but the nodes are destructive. The nodes are out of phase. The Doppler effect changes the, right? So the velocity of sound is constant, but if the observer or the source change, then the frequency seems to change. It also changes the wavelength, because if the frequency changes, the wavelength changes because the velocity is constant. But the only possible answer here is frequency, because wavelength isn't one of them. The speed of sound doesn't change. If you change the medium, the speed of sound changes. If the medium stays the same, the speed of sound stays the same. Frequency is determined by the source. If the source or the observer do not move, the frequency stays the same. If either of them move, the frequency changes by the Doppler effect. Bow waves are produced by waves of water moving faster, destructively interfering, moving slower than the source. So it's not asking about the source here, because before we were talking about the source movement, now it's talking about the wave movement, so they reversed it. The wave moves slower than the source is a bow wave. The first way I presented it, the source was moving faster than the wave. That's the same thing as saying that the wave is moving slower than the source. Shock waves are produced by waves of sound. So we have bow waves in water, shock waves in sound. And it's basically the same thing if you're moving faster. Um, oh, I forgot um, the whole of constructive interfering. I don't think I went over that part. This is a bad question because you could also say C, but the reason, I didn't actually say the reason. I should go back. Like, I don't think I said that now. Why? Let me show the waves. Why is it so loud along this crest? If you look at these waves, notice how all the way along this wave, you see the waves coming together. I don't know if you can see that. I'll try and make it bigger. All along the wave, that's where the waves are coming together. That's constructive interference. Okay? And because of that constructive interference happening there, you get a louder sound. Now I got to try and fix the size of this back. Okay? So it's not just if I can get back to this question, it's not just a matter of moving faster than the source producing them. That's true, and I think that's true too. So, but it's also constructive interference. So it's A and C basically there. That takes us to the end of the questions, the end of the notes for this chapter. If you have any questions, as always, send me an email.